This is also written in the form, it's the K that's on the right-hand side. Actually, I found that a source of considerable difficulty, and in general it is. It's for these, the temperature concentration model, it's natural to have the K on the right-hand side and to separate out the QE as part of it. Another model for which that's true is mixing, as I think I'll show you on Monday. On the other hand, there are some common first-order models for which it's not a natural way to separate things out. Examples would be the RC circuit, radioactive decay, stuff like that. So this is not of universal utility, but I thought that that form of writing it was of sufficient utility to make a special case and emphasize it very heavily in the notes. Let's look at the equation in this form will be good enough, the y prime. When you solve it, let me remind you that how the solutions look, because that explains the terminology. The solution looks like, after you've done the integrating factor and multiplied through and integrated both sides, you know, in short, what you're supposed to do. The solution looks like y equals, there's the term e to the negative k out front times an integral which you can either make definite or indefinite according to your preference. Q of t times e to the kt inside dt. It will help you to remember the opposite signs if you think that when q is a constant, 1 for example, you want these two guys to cancel out and produce a constant solution. That's a good way to remember that the signs have to be opposite. But I don't encourage you to remember the formula at all. It's just a convenient thing to be able to, for me to be able to use right now. And then there's the other term which comes by putting out the arbitrary constant explicitly, c e to the negative k, t. So you can either write it this way, where this is somewhat vague, or you can make it definite by putting a 0 here and a t there and change the dummy variable inside according to the way the notes tell you to do it. Now, when you do this, and if k is positive, that's absolutely essential, only when that is so, then this term, as I told you a week or so ago, this term goes to 0 because k is positive as t goes to infinity. So this goes to 0 as t goes, and it doesn't matter what c is as t goes to infinity. This term stays some sort of function. And so this term is called the steady state or long-term solution, or it's called both, the long-term solution. And this, which disappears, gets smaller and smaller as time goes on, is therefore called the transient, because it disappears as the time increases to infinity. So this part uses the initial condition, uses the initial value, let's call it y of 0, assuming that you started the initial value at t when t was equal to 0, which is a common thing to do, although not, of course, not necessary. The starting value appears in this term. This one is just some function. Now, the general picture of the way that looks is the steady state solution will be some solution like, I don't know, like that, let's say. So that's the steady state solution, the SSS. What do the other guys look like? Well, the steady state solution has this starting point. Other solutions can have any of these other starting points. So in the beginning, they won't look like the steady state solution, but we know that as time goes on, they must approach it, because this term represents the difference between the solution and the steady state solution. So this term is going to 0, and therefore whatever these guys do to start out with, after a while, they must follow the steady state solution more and more closely. They must, in short, be asymptotic to it. So the solutions to any equation of that form will look like this. Even if they, up here, maybe it started at 127, that's okay. After a while, it's going to start approaching that green curve. Of course, they won't cross each other, but they're sort of like a, that's the rock star, and these are the groupies trying to get close to it. Now, but something follows from that picture. Which is the truth? Which is the steady state solution? What, in short, is so special about this green curve? All these other white solution curves have that same property. The same property that all the other white curves and the green curve too are trying to get close to them. In other words, there is nothing special about the green curve. It's just that they all want to get close to each other. And therefore, there isn't, though you can write a formula like this, there isn't one steady state solution. There are many. Now, this produces vagueness, so you talk about the steady state solution. Which are you talking about? And I have no answer to that. Whichever one, the usual answer is whichever one looks simplest. Normally, the one that will look simplest is the one where c is 0. But if this is a peculiar function, it might be that for some other value of c, you get an even simpler expression. So the steady state solution, about the best I can say, either integrate that, don't use an arbitrary constant and use what you get, or pick the simplest. Pick the value of c, which gives you the simplest answer. Pick the simplest function. And call that's what's usually called the steady state solution. Now, from that point of view, what I'm calling the input in this input response point of view, which we're going to be using, by the way, constantly, well, pretty much all term long, but certainly for the next month or so, I'm constantly going to be coming back to it. The input is the Q of t. In other words, it seems rather peculiar, but the input is the right-hand side of the equation, of the differential equation, and the reason is because I'm always thinking of this temperature model. The external water bath at temperature T external, the internal thing here. The problem is, given this function, the external water bath temperature is driving, so to speak, the temperature of the inside. And therefore, the input is the temperature of the water bath. I don't like the word output, although it would be the natural thing, because this temperature doesn't look like an output. Anyone might be willing to say, yeah, you're inputting the value of the temperature here. It's more like the normal term is response. This thing is this plus the water bath is a little system, and the response of the system, i.e. the change in the internal temperature, is governed by the driving external temperature. So the input is Q of t, and the response of the system is the solution to the differential equation. Now, if the thing is special, as it's going to be for most of this period, if it has that special form, then I really want to call Q sub e the input. I want to call Q sub e the input, and there is no standard way of doing that, although there's a most common way. I'm just calling it the physical input. In other words, the temperature input or the concentration input. And that will be my Q E of t. And by the subscript e, you'll understand that I'm writing it in that form and thinking of this model, or a concentration model, or a mixing model, as I'll show you on Monday. By the way, this is often handled. I mean, how would you handle this to get rid of a k? Well, divide through by k. So this equation is often in the literature written this way. 1 over k times y prime plus y is equal to, well, now they call it q of t, not qe of t, because they've gotten rid of this funny factor. But I'll continue to call it qe. So in other words, in this part, this is just frankly called the input. One doesn't say physical or anything. And this is the solution, is then the response. And this funny coefficient of y prime, that's not in standard linear form, is it, anymore? But it's a standard form if you want to do this input response analysis. So this is also a way of writing the equation. I'm not going to use it because how many standard forms can this poor little course absorb? I'll stick to that one. Okay. You have then the superposition principle, which I don't think I'm going to. The solution, which solution? Well, normally it means any solution, or in other words, the steady state solution. Now notice that terminology only makes sense if k is positive. And in fact, there is nothing like, the picture doesn't look at all like this if k is negative, and therefore the terms would, steady state, transient, would be totally inappropriate if k were negative. So this assumes definitely that k has to be greater than 0. Otherwise, no. So I'll call this the physical input, and then you have the superposition principle, in which I really can't improve upon what's written on the notes. This superposition of inputs. Whether they're physical inputs or non-physical inputs, if the input q of t produces the response y of t, and q2 of t produces the response y2 of t, then a simple calculation with the differential equation shows you by, so to speak, adding that the sum of these two, I stated it very generally in the notes, but we'll have as the response y1, the steady state response y1 plus y2, and a constant times q1 we'll have as the response the constant times y1. That's an expression essentially of the linear. It uses the special form of the equation, and we'll have a very efficient and elegant way of seeing this when we study higher order equations. For now, the little calculation that's done in the notes will suffice for first order equations. If you don't have a complicated equation, there's no point in making a fuss over proofs using it. So, but it essentially uses the fact that the equation is linear, or that's bad, so linearity of the ODE. In other words, it's a consequence of the fact that the equation looks the way it does. And something like this would not in any sense be true if the equation, for example, had here a y squared instead of y. Everything I'm saying this period would be total nonsense and totally inapplicable. Now, today, what I wanted to discuss was what's in the notes that I gave you today, which is what happens when the physical input is trigonometric. For certain reasons, that's the most important case there is. It's because of the existence of what are called Fourier series, and there are a couple of words about them. That's something we'll be studying in about 3 weeks or so. But what's going on roughly is that, so I want the physical, so I'm going to take the equation in the form y prime plus ky equals k times qe of t. And the input that I'm interested in is when this is a simple one that you used on the visual that you got 2 points worth of work for handing in today, cosine omega t. So if you like, k here. So the QE is cosine omega t. That was the physical input. And omega, as you know, is, you have to be careful when you use the word frequency. I assume you got this from physics class last semester. But anyway, just to remind you, there's a whole yoga of 5 or 6 terms that go whenever you're talking about trigonometric functions. Instead of giving a long explanation, the end of the second page of the notes just gives you a reference list of what you're expected to know for 1803 and physics as well, with a brief 1 or 2 line description of what each of those means. So think of it as something to look up, refer back to if you've forgotten. But omega is what's called the angular frequency or the circular frequency. It's somewhat misleading to call it the frequency, although I probably will. It's the angular frequency. In other words, it's the number of complete oscillations. This cosine omega t is going up and down, right? So a complete oscillation is it goes down and then returns to where it started. That's a complete oscillation. This is only half an oscillation because you didn't give it a chance to get back. Okay, so the number of complete oscillations in how much time? Well, in 2 pi, in the distance 2 pi on the t-axis, in the interval of length 2 pi. Because, for example, if omega is 1, cosine t takes 2 pi to repeat itself, right? If omega were 2, it would repeat itself. It would make 2 complete oscillations in the interval 2 pi. So it's what happens in the interval 2 pi, not what happens in the time interval 1, which is the natural meaning of the word frequency. There's always this factor of 2 pi that floats around to make all your formulas and solutions incorrect. Okay, now, so what I'm out to do is, the problem is, for the physical input, QE, cosine omega t, find the response. In other words, solve the differential equation. In short, for the visual that you looked at, I think I've forgotten the colors now. The input was in green, maybe, but I do remember that the response is in yellow. I think I remember that. So find the response, yellow. And the input was, what color was it, green? Blue, blue. Light blue. Okay, so we got to solve the we got to solve the differential equation. Now, it's a question of how I'm going to solve the differential equation. I'm going to use complex numbers throughout. A, because that's the way it's usually done. B, to give you practice using complex numbers. And I don't think I need any other reasons. So I'm going to use complex numbers. I'm going to complexify. To use complex numbers, what you do is complexification of the problem. So I'm going to complexify the problem. Turn it into the domain of complex numbers. So take the differential equation, turn it into a differential equation involving complex numbers, solve that, and then go back to the real domain to get the answer. Since it's easier to integrate exponentials. And therefore, try to change the trigonometric functions into complex exponentials simply because the work will be easier to do. All right, so let's do it. To change this differential equation, remember I've got cosine omega t here. I'm going to use the fact that e to the I omega t, Euler's formula, that the real part of it is cosine omega t. So I'm going to view this as the real part of this complex function, but I'll throw in the imaginary part too, since at one point we'll need it. Now, what is the equation then that it's going to turn into? Sorry. the complexified equation is going to be y prime plus ky equals, and now instead of the right-hand side, k